Electric field is an important concept. It is actually a concept. It was introduced by scientists to understand the Coulomb's law better. But then it has various different uses. It is a concept in which it is believed that when there is a charge or a charged body, then around this charged body, a region has some kind of magical capability which can produce force on any other charge. So in one way, electric field is just a region, around a charged body. Let me put it in this way. Suppose there is a charged body with charge positive Q, capital Q. Then if we bring any other charge, let's say small q, this is another charge, within the region of this big charge body, then this small charge q will feel a force. And this feeling of force is just because of there is something else there in that region that is called the electric field, which is denoted by E. And since it is a vector, we just put an arrow over it. Electric field is because of the charge at the origin and not because of the charge we bring in that region. So even if we remove the charge, what we have brought in the region, even then the electric field will be there. It will remain be there. So we can say that it is an invisible force experienced by any charge brought near a different charge body. Let's check the formula for electric field, which says that it is E is equal to 1 upon 4 pi epsilon naught Q, capital Q, by R square. Here R is the distance between the two charges, or we can say that R is the distance between the charge at the origin and any point in the space where we want to find the electric field. Now here we only focus on the capital Q, the charge at the origin. So in the formula, capital Q is there, but not the small q, means no other charge is required. Hence, the electric field depends only on the charge at the origin. And if we analyze the formula for force, that is F is equal to 1 upon 4 pi epsilon naught capital Q multiplied by small q and divided by R square, which simply means from here we can see that electric field is actually force upon the test charge or the charge brought in that region. These are vectors. Just for your understanding, I have removed the vector sign for now. Or from here we can imply that force is actually small q, that is the charge, multiplied by the electric field. And what you can see here in the picture is that there is charge q, and we can see that there are lines drawn. So these lines are just the representation of the electric field. So just to represent it in on a paper, graphical representation, that's it. And you see the arrows. I'm sorry, we have to go back. And the arrows, what you can see, these arrows are outward because it is a positive charge. That's why the lines which represent the electric field has arrow pointing outward. And when the charge is negative, we have the same lines, but the arrows are inward towards the point of origin. or towards the charge minus q. Now let us do the definition. The definition of electric field is something like this. Electric field due to a charge capital Q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. In the definition, there is a charge capital Q which is somewhere, and electric field at any point, let's say any other point, let's say this point is P, and at this point P the electric field is actually the force experienced by a unit positive charge. Okay, unit positive charge means, unit means 1, the value of the charge is 1 and it is positive. So if we bring a very small positive charge near this region or at a point P, then the force experienced by this small positive charge, unit positive charge, is actually electric field at that point. So electric field will be experienced right at the point P. Interestingly, the field actually is experienced by the charge at origin as well, or at the point of origin as well, by the capital Q charge. So as we know that at point P, if a unit positive charge small q is brought, then this charge will feel a kind of a force due to the capital Q. The same way, capital Q will feel a force because of small q at point O, at point origin. So if you want to try to draw the kind of the field, what happens here, so if these are the field lines because of capital Q, there will be field lines because of small q as well. Alright, so it means both the charges, any charge in the space will create a field around it, create a space around it where the force can be felt. We have discussed that for the capital Q there will be an electric field, and for small q there will be another electric field. Okay, so in the region there are two different electric fields because of two charges. Now if we bring very strong small q in the region, then the position of the capital Q will not be fixed because of the force exerted by this small q. The position of the capital Q charge might get changed. It might get displaced, maybe pushed away. So, and in that way, it will be very difficult to find the exact value of electric field, because the r here, the distance between these 2 points, it will not be fixed, it will shift. That's why the concept of test charge is introduced. The concept of test charge says that we have to bring the charge, the extra charge in the region of the capital Q so small that it won't affect the position of capital Q. Okay, so that should be very small. That's why if you see in the formula, E is actually limiting the value of the test charge or small q approaching to 0, means take the test charge so small, reaching to 0, the value of the test charge should be so small that it should not affect the electric field, okay, due to the capital Q. So now E is equal to limit q tends to 0, and that is F by small q. So as I told you, a practical way to get around the problem that we should not change the value here. So we have to keep q undisturbed in the presence of small q, and for that we need to take small q literally tending towards 0. Electric field due to a system of charges. For that, let us see the picture. So suppose there is one charge q1 here, then there is another charge q2, and then q3. So there are many charges. And because of all these charges, if we want to find the electric field at certain point in space, so let this point be P, and let other points be A, B, and C, where the charges are placed. So all these vectors, radial vectors, can be named as R1, R2, R3. So at P, the electric field due to all these charges is actually the vector sum of the individual electric fields that we have done when we were dealing with force as well, and that was called the superposition principle, if you remember. So electric field E at P is actually electric field at P due to charge 1, that is R1, plus electric field at P due to second charge, which is R2 distance away, and then plus E3, R3, and so on. So what we have done here is actually due to Q1, the electric field will be in this direction maybe, and due to Q2, the direction of electric field will be this, and for Q3 the direction will be this, and we have now 3 vectors, and total electric field, suppose that is E, and for that E we actually have to add E1 plus E2 plus E3, and these are not simple arithmetic or addition, these are vector additions. So this is what we have to do to find electric field due to a system of charges. Let us understand this example 1.8. So there are 2 charges given, Q1 and Q2, and we need to find electric field at A, B, and C. At these 3 points we have to find the electric field due to these charges. So all we need to do here is, first of all, we need to do this formula that actually electric field is 1 upon 4 pi epsilon naught q charge upon the distance square, r square, okay, and it is a vector. As you can see in the example, the charges q1 and q2 have the values plus 10 to the power minus 8 coulomb and minus 10 to the power minus 8 coulomb. So one is positive charge and other one is negative charge. Now the distances are also given. So here you can see from Q1 the point A is 0.05 meter away, and from Q2 it is the same distance away, 0.05. So the values are given. R is given, R is 0.05 meter, and charges Q1 is equal to plus 10 to the power minus 8 coulomb, and Q2 is minus 10 to the power minus 8 coulomb. And as we have discussed, E is actually E1 plus E2, electric field due to Q1 and electric field due to Q2, but these are vectors, so we have to take direction in consideration. And also keep in mind that 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So when you plug in all these values, whatever values we have put here, then what do we get? We get for first charge, this is the value of electric field. And same is for the second charge, but it is all about the directions are different. So just think about it. If Q1 is positive charge, as we have discussed, Q1 is positive, then the electric field is outward. So the direction is this side. All right. And for Q2 being negative, the direction is again towards the charge. So both the directions are same. That's why you can see here the direction is only towards Q2. Now at point B, the direction of the electric field due to Q1 is outward from Q1, but at B, the direction of the electric field due to Q2 is actually towards Q2, because Q2 is a negative charge. So negative charge electric field is towards the charge. All right. So whatever value you get, because here the distance of Q1 and B is only this much, but distance of Q2 and B, Q2 and B is this long. So we will add all these three and that big distance will be there. So the value of the electric field due to Q2 will be different, and you just add these two values. So as you can see, for electric field at B due to Q1 is 3.6 that we have found earlier, same value actually, but due to Q2 the value is different, and one is positive, one is negative, because one is the negative charge. And actually what is happening here, total electric field is E1B minus E2B. So when you subtract, you actually get this value. Okay. And since this is a positive value, that's why it is directed towards left. Why it is directed towards left? Because positive means it is the positive charge. Q1 is the prominent charge, so that's why overall electric field is towards the left. And for the point C, we have to actually focus on this distance. Both the distances are same, and it is just that, sorry, let me make it a bit clear. So here for point C, what is happening is because of the Q1 positive charge, the electric field is outward, and because of Q2 negative charge, the electric field is inward towards Q2. So one, as you can see, due to Q1 it is this, due to Q2 this is this direction, and one is called E1C, I mean electric field at C due to charge 1, and E2C, electric field at C due to charge Q2. And if we add these two vectors, the electric field will be somewhere in between these two vectors. That is the rule that you have learnt in class 11th mathematics and physics. So here also individually we have to find the electric fields, and then vector sum of this electric fields will give the total electric field at C. Alright, and the direction is on the right hand side. And here, as you can see, E1c and E2c have the same values, but because of the directions, we have to take this vector sum, and here there are angles which matters. So this angle and this angles matter. That's why this is cos pi by 3 what it has been used for the vector sum, and finally we get this value. Now if you have confusion in these cos pi by 3 and cos pi by 3 what is used here, it is simply, I just let you know for someone who has this confusion. So we had this E1, this E2. We actually want to project E1 on the horizontal line, and to do that we can do it by multiplying it by cos pi by 3. Why pi by 3? Because this is an equilateral triangle, so the angles are actually pi by 3. All the angles are pi by 3, that is 60 degree. So the projection of E1 on the horizontal line, that is the direction of the final electric field, is E1 cos pi by 3, and for E2 also it will be E2 cos pi by 3, and the projection will be here on this. That's why we are adding E1 cos pi by 3, E2 cos pi by 3 here, what you can see. Alright. Let us quickly do electric field lines. Electric field lines are just the representation of electric field. So we want to visualize it, how electric fields looks like. That's why we are using electric field lines. These are not actual lines. These are just the representation, just to show, and it works very scientifically and it works accurately in a way. I'll just show you how it works. So if there is a positive charge, the field lines are there and it is directed radially outward. So radius, outward radius. This is the representation of electric field lines. So electric field lines actually shows that around the region of the charge there is field. There is some kind of capability that can exert force on any charge coming in that region. Okay. And if the charges are negative, if the charge is negative, then the same radial lines will be there, but it will be directed inward. Okay. So that's the difference. Negative charge inward. Why? Because when we talk about negative charge, we actually mean extra electrons, means taking more electrons. So that's why inward, and positive charge means giving electron to other charges, okay, other bodies, means radially outward. Outward means giving electron, and inward means taking electron. Okay, so that's why positive means outward, negative means inward. Now, using these electric field lines, you can talk about the strength of electric field also. So we can talk about stronger electric field or less electric field, or inferior electric field. So suppose if we come close to the source charge, the electric field is more stronger, which simply can be depicted by number of lines. There are more lines in a particular region. Okay, the same region if drawn somewhere else farther, then less lines are crossing this sphere, which simply means less lines means weaker electric field. More lines in that the same area means stronger electric field. Because formula of electric field is 1/4 pi epsilon naught Q upon R1 square or R square, for example. So in this case, if you are closer to the charge, it means the denominator is lesser, means the whole quantity will be more. So that's why closer to the charge means less value of R. Less value of R gives more value of Q. Sorry, more value of E. So if you go farther from the charge, then the electric field will be weaker, because the R is longer. If we go farther, R is longer, so the value of R increases, the value of E will decrease. Okay, because E is inversely proportional to the square of the distance. Faraday called it the line of forces, but the better description is field lines. So we use field lines, and this is what we are adopting in this book. Alright, now these are the final things about field lines. There are 4 things that you need to keep in mind. The field lines follow some important general properties. What are the properties? That field lines start from positive charge and end at the negative charge. Okay, start from the positive charge, okay, and end at the negative charge. So if you see here, it starts from the positive charge and end at the negative charge. So this is the arrow sign. Okay, if there is a single charge, they may start or end at infinity. So if there is only single charge, as you can see here, it might start at the origin, end at the infinity, or start at the infinity and end at the origin, depending upon what kind of charge it is. If it is positive, then it will start at the origin and end at the infinity. Okay, and if it is negative, then it will start at the origin and end at the origin. It will start at the infinity and end at the origin. Alright, the second property is, in a charge-free region, electric field lines can be taken to be continuous curve without any breaks. Or simply, electric field lines can be taken to be continuous curves without any break. So there is no break. It will just go. There is no break actually, okay? 2 field lines can never cross each other. So whatever you are seeing here, let me show you here in this picture. So if there are 2 field lines we're talking about, one is this, another one is this, they will never cross each other. They will never intersect. So these 2 lines, if they are going, it will never happen that they will cross each other. Why? Because field lines at a particular point gives a particular direction of electric field. Okay. So if they cross at each other, field lines give you the direction. So if they cross at each other, means at the same point, the tangent of this field line will give one direction, the tangent of this field line will give another direction. At the same point, there cannot be 2 directions of the electric field. That's why electric field never intersect each other. So if they did, the field at that point, a point of intersection, will not have a unique direction. So it has always unique direction. That's what we need to keep in mind. At one point, there will be only one direction of the electric field in that region. So that's why at one point, if more electric field lines intersect, it will give multiple directions, and which is absurd. Okay. And the 4th property is, electrostatic field lines do not form any closed loop. So you will never see anything like that electric field lines are coming and then making a closed loop. Nothing like this will happen with electric field lines. So these are the 4 properties, and that is the end of electric field lines. And in next part we will discuss electric flux. Thank you.